I'd like to get my attention and we'll go on. I'm going to talk first about basic soils. Why do we talk about soil? Well, we put nutrients on soil and we grow animals on soil. And so soil is our basic foundation in a sense of this whole nutrient management thing. So our first segment today will be soil. So what do people think of soil? Well, it depends upon who you are. I bet if I ask each of you to give me a definition of soil, I would get quite a collection. Geologists tend to just see it as the outer layer of the earth. They're more interested in what's underneath. There was a writer who wrote a book on soil about 10, 12 years ago. He called it the ecstatic skin of the earth. Okay? Lots of gardeners just think of it as that stuff near the soil surface that grows their plants well. Daniel Halal, a soil physicist, a very famous soil physicist, has a new book on soils, and he calls it the crucible of terrestrial life. Now, if a crucible is a vessel in which a lot of stuff happens, you know, his terminology there has a lot of symbolism in it. And ecologists now tend to think of it as the pedosphere. We recognize the fact that there's the hard earth below us, the lithosphere, the rocks, the hydrosphere, the water cycle, the atmosphere, and that pedosphere of the soil is that interface where they all come together. Okay? Now, I'm going to take a slightly different and much more chemically geared ecological approach. I'm going to tell you that it's a dynamic, which means it changes rapidly, reactive, stuff happens, three-phase system. Three phases being solid, liquid, and gas. Now, by the way, how many people here have had a soils class in high school FFA or college or something? Okay. A lot of people. Okay. Oh, of course. Okay. Here's a two-dimensional picture of a soil, just to kind of get us oriented. We've got some big particles. We've got some clumps of smaller particles. We've got roots. We've got animals. Can you see the blue as opposed to the white back there? Does that show up today? Okay. We've got water films around particles. Some pores are actually filled with water. Some aren't. We'll reflect back on almost all these things during our discussion today. One of the most beautiful drawings of soil I've ever seen. And the first thing we're going to talk about, back to this a second. See this diagram? This is the pie chart, okay? Approximately, in topsoil, about half of your soil is soil solids. And of those solids, typically you have far more mineral or inorganic components than you do organic components. The other half of a topsoil or a well-managed agricultural soil will be pore space or void space, and several days after rainfall or irrigation there should be approximately a 50-50 split between air and water. Okay? Now this is what I refer to as the pie chart diagram for soil. It's what we'll start off looking at today, and then as we fine-tune our concepts we'll build a more complicated model. So those mineral or inorganic solids are classified based on their particle size, and the organic solids are much more complicated, and I'll show you a way that we can look at them also. For the mineral or the inorganic parts in soil, we typically classify the smaller components as either sand, silts, and clays. There is a classification system for the bigger stuff, stones, cobbles, rocks, but we're not going to go there today. We're just going to talk about sands, silts, and clays. You can see the size, dimensions here, and in terms of how they feel, and if you've ever done texture by feel, how they feel is important. The sands tend to be gritty, okay? The silts tend to feel like flour or cornstarch or talcum powder. They have a smoothness to them, okay? Whereas the clays are sticky, okay? So if you got a silt wet, it would feel like cornstarch or body powder, talcum powder, whereas if you got a clay sticky, it would feel gluey. Your fingers would almost stick together. And sands, of course, they're just gritty, wet or dry. Okay? And since soils usually are a combination of particle sizes, the textural triangle is a way of giving a name to soils depending upon what proportion of sand, silt, and clay-sized particles they have. Okay? So you can see that this side of the triangle is sand from 0 to 100. This side of the triangle is clay from 0 to 100. That side of the triangle is silt from 0 to 100, and if you knew the sand, silt, and clay content of your soil, you could find out where those three things intersect on this triangle, and you would know what your textural class is. So as this triangle is set up, your sandy soils are down in this corner, your loams are typically in the middle, you've got silties over here, and along the top of the textural triangle you've got your clay textural classes. Now a textural class describes the proportion of the sand, silt, and clay-sized particles you have. Okay. Oftentimes we break down the textural triangle even more so that we can make some generalized statements about things. And this corner down here that's dominated by the sands, loamy sands, sandy loams, are often called coarse textured soils. You'll hear people describe their soils like that. Things where the clay properties dominate the way the soil behaves and feels are called the fine textured soils. And then this tier here, from sandy clay loams through the silts, are often called the medium textured soils. And we can make some generalizations about them in terms of a lot of the properties that we might be interested in. Water holding capacity, for example, is just as important as nutrient holding capacity to get a good crop. It needs nutrients, it needs water. Water holding capacity tends to be low in coarse textured soils, and medium textured soils, and high in fine textured soils. Okay? Water holding capacity and nutrient retention capacity are highly related. The things that lead to one lead to the other. Okay? So we know the same things about nutrient holding capacity as we do water. It's low in coarse textured soils like sandy loams, loamy sands. It's moderate in a loam or silt loam, and it's high in a clay, silty clay loam, clay loam. Leaching potential, on the other hand, the propensity for something to move through a soil, not be retained by it, is inversely related. Okay? If it's low in water holding capacity and in nutrient holding capacity, it's high in leaching potential. And all these things make sense when we start to think about it. The one that's really different is the susceptibility to erosion. It turns out that silt-sized particles are very erodible. They're easy to erode. Sand is heavy and it's harder to move with wind or water because of its weight. Clays tend to stick together into bigger clumps, but the silts just kind of melt apart. And so the one real exception to this relationship and inverse relationship is the susceptibility to erosion, where the medium textured soils that have more silt in them tend to be the most prone to erosion compared to either the sands or the clays. Okay? So let's think about this in terms of a question. Remember, you're not only preparing yourself ultimately to do nutrient management plans, but before you can do that, you have to pass a 100-question multiple choice exam. So I'm going to throw in some ideas that could be framed as questions. Okay? So the physical property that describes the proportion of sand, silt, and clay-sized particles in a soil is called what? A, structure, B, texture, C, bulk density, or D, porosity? What's our answer here? Texture. Okay? This is, in fact, the definition of texture. Now, the property that describes how particles are arranged into aggregates is called texture, porosity, structure, or particle density. What do you think? Think back to your soils. Remember? Structure. This is what we call structure. And texture and structure are often confused by people. Okay? Texture just tells you how much sand, silt, and clay you've got. Okay? Structure is how those particles are arranged. They're two very different properties. A lot of times we describe structure by the shape of the unit. We're not going to go into too much detail on this here. So here's a question for you. How does organic matter affect soil texture? Think back to the definition. How does organic matter affect soil texture? Texture is the proportion of sand, silt, and clay-sized mineral particles in your soil. How does organic matter affect that? Hold that thought. And then, how does organic matter affect soil structure? Let's go back to the first one. How does organic matter affect texture? Huh? I guess the more basic question is, does it affect soil texture? And the answer is no. Okay? If by definition texture is the proportion of sand, silt, and clay-sized mineral particles, organic matter is irrelevant. Okay? Again, often confused. Whereas organic matter has a phenomenal effect on soil structure. How particles arrange themselves, how much space is between them, how hard they're held together. Organic matter is critically important in the development of these aggregates or beds or clods that make up soil structure. Okay? Okay, so let's talk about organic matter a little. We don't talk about organic matter in terms of the size of the particle. We talk about it in terms of how alive or dead it is, essentially. And you can see from our little organic matter pie chart that in most topsoils, humus makes up more of the organic matter in your soil than the other two components. Biomass, this is everything that's alive in soil, makes up about 10% of the organic matter. And the rest is residues and byproducts, stuff you can see. If you looked under a microscope, you could identify what it is, or you could do a chemical analysis and find that it's a fairly simple material. Okay? So unlike particle size, which is the discriminator for mineral components in soil, organic matter is quite different. Now, this whole notion of splitting it up into these three pools, so to speak, is an evolution of some ideas put out there by Fred Magdoff in a book he wrote, Building Soils for Better Crops. And he actually called the three categories the living, the dead, and the very dead. Okay? I'm going to call them humus, biomass, and residues and byproducts. It's a little bit more precise. Okay, so let's talk about what the biomass is. First of all, it's everything in the soil that's alive now. Right? It consists of a huge range of creatures, everything from viruses that we need an electron microscope to see, up through the stuff we can see with our unaided eye, and everything in between. I like to think of them as the microbes, the things we need some kind of a microscope to see, the mesobes, the things I could see with a hand lens, and the macrobes, stuff I can see with my glasses on, okay? So like worms and centipedes and larvae of beetles and stuff like that. Everything that is alive in the soil. That's what it is. Actually, there are very complicated food webs in soil, just like there are on the land. You know, you've got creature A that's eaten by creature B, that's eaten by creature C, that's that whole food web we don't call them food chains anymore, we call them food webs. And in fact, there's very complicated food webs in soil. Start out by plants, of course, fixing photosynthate as part of photosynthesis, kind of charging your below ground ecosystem, but there's creatures that eat the stuff that comes out of the roots or eat the roots. There's bacteria that break it down. You can see that the protozoa like the bacteria. It's a vicious world under the ground, just like it is above the ground. Okay? So what does biomass do? Well, the creatures in soil participate in nutrient cycling. They basically break down plant and animal material, or the residues that I was talking about. They use what they need and they leave behind what they don't. They're not breaking it down out of the goodness of their heart, so to speak. They're breaking it down because they need it. They have an enzyme that they produce that can break down something out in the soil system that they need for their nutrition. And so two processes that Dr. McGrath will talk about tomorrow, immobilization and mineralization, both talk about what biomass does in terms of nutrient cycle. In terms of mineralization, that's the term we use to describe microbes breaking down stuff into a mineral form. Okay? They took what they needed and they left some behind that plants can now use. Whereas immobilization is when they take nutrients out of the soil, tie it up in their microbodies or their macrobodies, and it's not available for the plants to use because it's tied up in some other creature's body right now until they die and it breaks down. And there's this dance going on in soil all the time between mineralization and immobilization, and you can affect that by what you do in terms of adding organic resources or crop residues or stuff like that. Another very important thing biomass does, and this is particularly true of the bigger organisms, creates biopores. These bigger creatures move through soil, they move stuff apart. In the case of worms, they actually eat their way through it. They create channels or pores in the soil. We call those biopores. A lot of the pores in soil are actually biopores. And these channels promote water infiltration, and they also create a healthy balance between big pores and small pores, large pores and small pores. Now that's important because it's those large pores, which we call macropores, which allow the rapid infiltration of rainfall as opposed to running off, and which allow the replenishment of oxygen in the root zone. Now, of course, it's also important to have the micropores. That's where water is stored that plants can use between rainfall events. So you want a balance between these two. You don't want all or nothing. Okay, residues and byproducts. This is the dead stuff. It could be crop residue. It could be dead roots. It could be the bodies of soil creatures whose lifespans are over. And then there's the byproducts. These are materials that plant roots and soil creatures release or exude into the soil as part of life. Now, I like to say it's sort of like sweating, but it's actually much more complicated than that. But we exude stuff too. Stuff comes out of our skin. Well, it comes out of roots and soil creatures' bodies too. Those materials are rich in easily digestible materials that other creatures can use. Actually, a zone around a root, they call it the rhizosphere, has a high concentration of root exudates, and it's probably the most microbially dense place in the soil because there's all that good stuff to eat. Bacteria love it. So what do? What do residues and byproducts do? They are the fuel and the nutrient source for most of the soil organisms. Soil organisms need energy just like we do, and they need nutrients. And residues and byproducts are where they get that. Another very important function, though, is the fact that many of the byproducts have a sticky or a gummy nature. So as the residues are breaking down and as the microbes are living, they're exuding these materials that actually hold soil particles together into clumps or aggregates or PEDs. Right? So it's very important if we want to maintain good soil structure and a good balance between macropores and micropores to have a constant supply of residues and byproducts in our soil so that we keep our microbial population active and happy and continually forming these kinds of materials that hold particles together. Humus. So what is it? Remember, it makes up the majority of the organic matter in a topsoil. It's the relatively stable end product of residue decomposition. Okay? Makes up the most of the organic matter. It resists further decomposition. People who have studied it believe that it only breaks down about 1% a year, whereas a residue can break down 70, 80, 90% the first year. It is not a good nutrient source or energy source for soil creatures because not much of it's going to break down. In a sense, what the creatures could use has already been taken from it before it got to this point. These are, there's several schools of thought about how humus forms, and I don't care to take sides, but it appears that it's the result of the polymerization of resistant molecules with some new stuff added. What does it do? Well, we said it wasn't a very good nutrient or fuel source, but it's very small in particle size, it's very high in surface area, and it has many charged locations on it. It's also very effective at holding water. So it's a great nutrient-holding material, it's a great water-holding material, but it's not a good nutrient source. Well, the residues are a good nutrient source, and they don't hold much water. Humus is what holds water and nutrients, but it isn't a good nutrient and energy source. You need all of them in the right proportion to keep things humming the way you want to. Okay? Well, let's switch now and talk about what isn't solid. Talk about what's in the pores. Some books call this the void space. Some people don't like that term because void means nothing, and obviously there's something here, but whatever. The British tend to like void space. You pick up a British book, you'll see them call it void. So what's in the pores? Well, one of two things, soil water or soil air. Okay? Soil water, we want there to be enough of it so that our plants aren't water stressed. We also want the water in the soil, or what we call the soil solution, to have an adequate supply of nutrients. And we certainly want to minimize the loss of that water by either runoff or leaching if we can. Right? Soil air, on the other hand, is the source of oxygen for roots and the aerobic soil organisms. And it needs to be constantly enriched with oxygen because carbon dioxide is always being released and oxygen used up. We need to get oxygen back in the soil and carbon dioxide out. Okay. Here's a comparison of what the gases in the atmosphere and the soil air look like. This would be a well-structured topsoil several days after rainfall. Well-structured, I'm implying that there's a good balance between the macropores and the micropores. Several days after rainfall means that the big pores have drained. Okay, so we've got pretty good exchange. You can see that nitrogen really isn't affected. Oxygen is slightly less in the soil air than it is in what I'll call the ambient atmosphere. And the carbon dioxide levels are enriched in the soil air. Why? Because you've got creatures down there living, right? respiring just like we are. We're all giving off carbon dioxide too. Roots are, everything living in the soil is. And since it's a rather tortuous path between the soil pores and the above ground atmosphere, the exchange isn't perfect, okay? So there is a buildup of carbon dioxide. Now, if your soil was poorly structured or not well drained, you could see your oxygen drop down to 1-2%, maybe even close to 0, and this could go up very, very high. But in this case, a well-structured soil, a couple days after rainfall, there's not a huge difference. There's a difference, but it's not cataclysmic in terms of who's living there and whether or not they can survive. Here's a nice little diagram, and this is from Hillel's book, the guy that thinks soils are the crucible of terrestrial life, Dr. Hillel. And this is from his new book on soils, and he talks about soil aeration, and that's the exchange of oxygen and carbon dioxide between the soil pores and the ambient atmosphere. And we must have that to keep our aerobic organisms and our roots alive. They are using up oxygen, they're giving off carbon dioxide, so the CO2 needs to move out to the atmosphere. Because it's higher here and lower here, it'll do that if there's a way, and the oxygen needs to diffuse back in. That aeration is that exchange of gases between the soil atmosphere and the ambient atmosphere. Okay, we want a balance between water and air. That means we need a balance between macropores and micropores. The macropores drain quickly after rainfall or irrigation. They're important. Yeah, you lose the water that's in them, but they're the conduits for gas exchange, which we also need. The micropores hold water against the force of gravity, and after gravity's taken all the water it can away, it is still there. And some of that water, though not all, is plant available. Some isn't. And I'll talk a little bit about biological water a little bit later in this talk. Okay, there are some relationships between texture and pore space, or porosity. Let's talk about those for a minute. Here we've got sands on the left side, loam in the center, clays on the right. And first of all, we've got a line here that says total pore space. Top, you can see that sands have less total pore space than loams, and they have less than clays in terms of total pore space. But let's look at the size of the pores. In terms of the large pores, the pores which will drain quickly against the force of gravity, the sands have a lot of large pores. Loam have fewer. Clays have very few. It's actually a problem managing soil tying clay. If you don't manage your residues and your organic matter well, you can get so few macropores, you have trouble with aeration, and your plants perhaps won't grow well because basically an inadequate supply of oxygen to the roots. And the inverse is happening with the small pores. Sands have very few small pores which hold water, hence they're drouthy, okay? But clays have a preponderance of small pores. So there's a very definite relationship between texture and porosity. Again, it's nice to be in the middle. Loamy soils, medium textured soils tend to have a better balance between the small pores and the large pores. They're not drouthy like the sands, and they're not poorly aerated as some of the clays can be, particularly if they're not well managed. Another question. The soil physical property that describes the proportion of void space in a soil is called A, structure, B, texture, C, porosity, or D, bulk density. What do you think? Porosity. The answer is D, porosity. Okay. So we talked some about density of soil. How much does a soil weigh? What is its density? Density is just weight per unit volume. If you're going to talk about the weight of something, you've got to agree on what the volume is. And there are two ways of expressing density in soil, bulk density and particle density. And then, of course, we have two ways of expressing things in this universe. We have our English units, pounds per cubic foot, and metric units of grams per cubic centimeter. Okay, I'll tend to use the metric ones because I think in that right now. Bulk density is the density of the whole soil, solids and the pores, whereas particle density is the density of the soil solids only. You might wonder why we worry about particle density, but you'll see where it comes into play here in a few minutes. In terms of typical densities, expressed as grams per cubic centimeter, organic material is lighter, and organic soils, being things like peats and mucks, have very low density. They're very light. Okay? 10th to a 6th gram per cubic centimeter. Volcanic soils are also very light. We've got some volcanic soils in the United States, 0.6 to 0.8. Forest and native grasslands hover up about 1, 0.8 to 1.1. There's a difference between textural classes when they're cultivated. Cultivated silt loams tend to be less dense than cultivated sandy loams, which tend to be more dense. And then if you actually have a pan, whether it's a plow pan or a natural pan, you get very, very dense. And I point that out because most studies have shown that when the density gets to 1.6 or above, your roots aren't going to penetrate it. Whether it's the amount of force the roots have to exert or whether it's the fact that there's no oxygen there, I don't think that question's been answered, but they're not going to go through it. Okay, so the physical property that describes the density of the whole soil, both the solids and the voids, is called A, texture, B, structure, C, particle density, D, bulk density. Whole soil, bulk, okay, bulk density. Whereas the physical property that describes the density of the soil solids only is which? Particle density, which is like specific gravity if you're more comfortable with that term. Now, density is something that's commonly studied in soils, not necessarily in a soil test sense, but if you're, for a variety of other applications, density needs to be known. I'm just going to give you an example here. A soil pad, this is like a clod, think of this as a clod, has a volume of 124 cubic centimeters and a dry weight of 138 grams. What is its bulk density? This is a fair game for the exam. Okay, remember, a density is grams per cubic centimeter, weight per unit volume, right? It's also dry weight. Now, in this example, I gave you the dry weight. You may or may not be given the dry weight on the exam. But basically, the bulk density is the dry weight divided by the volume. If you have pounds per cubic foot, use that data. If you have grams per cubic centimeter, use that. In this example, we were given the data in the metric form, so it's 138 grams divided by 124 cubic centimeters. It's 1.1 grams, 0.11 grams per cubic centimeter. That's a good bulk density for a topsoil. Wouldn't get upset about that. And one reason why we also need to know the particle density of soil is because if we want to calculate the pore space, the most common way of doing it is to use the relationship between bulk density and particle density. Basically, pore space is 100 times minus the solid space, so it's 100 minus the relationship bulk density divided by particle density times 100. This is another one you want to know for the exam. And this is all in that Mid-Atlantic book on the disc that you have also. So let's look at an example. A very compacted plow pan has a density of 1.74 grams per cubic centimeter and a particle density of 2.68 grams per cubic centimeter. What is its porosity? Well, it's 100 minus the quantity bulk density divided by particle density times 100. So it's 100 minus 65 or 35. Okay. Remember we said that above about 1.6 roots don't grow? Well, 35% pore space isn't much. Okay. Could be an oxygen problem here. Okay, if you're ever given a situation where you're given a wet weight, but you know how much water is there, you're told how much water is there, you can figure out the dry weight. In this case, realize that the percent moisture in something is the weight of the water divided by the even-dry soil weight times 100. Virtually all calculations in soil are given on a dry weight basis, not a wet weight basis. So knowing how to figure out the percent moisture and how to figure out the dry weight is something that you might have to do. We'll talk more about exam strategy tomorrow, but got to decide where you're going to put your time. Talk a little bit about the soil solution. I'll talk a lot more about that later. You want enough water there. You want an adequate supply of water. You want it well supplied with nutrients. You want no limiting factors there. And you want to minimize the adverse conditions for plant growth. Now, in our climate, the adverse condition is usually acidity. If you go out west of the center part of the country, west of the Mississippi, and drier areas where there's not as much rainfall, the most common condition of the soil solution that's adverse would be salinity. Yes, there might be some places in Maryland where people are farming near tidal areas and all. I saw a soil analysis last week where soil had a tremendously high level of salts and of sodium. So there's some conditions where some people must be farming land that has some tidal influences of brackish water. but it's not common. Now, Gary Felton's going to talk a lot more about the water cycle. I just want to talk a little bit about the biological classes of water. Remember I said that the water that was in the micropore space was partially available and partially not available. Okay, some of it's held too tight for the plant roots to take it up. So let's have this little discussion. First of all, it rains, and all the pores are filled with water. Let's say we got 2 inches of rain like we did one day last week. Okay? All the pores are filled with water. We described that situation as saturation, and that's what it means by definition. All the pores are filled with water. But once the water ceases to come and the soil has a chance to drain, gravity will pull some of that water through, and the macropores will become empty of water. Well, that's good because you need the exchange of oxygen and carbon dioxide. And at the point where gravity doesn't drain any more water from the macropores, we call the condition field capacity. Now at that point, the micropores are filled with water. The macropores are empty of water. It's warm season. Plants are growing. Some water evaporates. Plants transpire a lot. Plants can use the water down to the point of wilting point. They get to a point where they will permanently wilt. They've taken all the water they can. Even if you water them again, they've gone too far. Okay. Some books call that permanent wilting point. This graphic calls it wilting point. So the water between saturation and field capacity is often called excess water or gravitational water. All right? It doesn't stay around very long. It's going to be gone in a couple days anyway. It's not really great anyway because it's blocking the pores from gas exchange. The available water, the water available for plant growth, is the water between field capacity and wilting point. If the water's held tighter than wilting point, it isn't going to do your crops any good. So that little diagram on the bottom is showing in this particular example where a soil has 40 milliliters of water at saturation, and at field capacity, about half that water is drained, excess or gravitational water. Okay? Of that 20 mils that it held against the force of gravity, only about 10 mils is held loosely enough that your plants can compete for it. Now, is the soil absolutely dry at wilting point? No, there's still water there, and if you were to put it in an oven and heat it to above boiling, you could drive it off. But it's held with too great a force for your plants to be able to utilize. So we have excess or gravitational water, we have available water, the water between field capacity and wilting point, and then that category of water that's held too tightly is called unavailable water. Here's another way of looking at that, a graph. Okay, you can, and this is giving you available water as a function of texture, where the percent clay in the soil is at the bottom. You can see that sands have a modest amount of available water, the water between field capacity and wilting point. Okay, they don't have much at wilting point because they don't have many tiny pores. Okay, other clay soils at the other extreme have a little bit more available water, but actually not much more than the sand. And look at the textural classes that have the most available water. Again, it's those loams, right? Better balance between large pores and small pores. Lots of pores, more pores than the sands, more pores that can carry water in an available form. I don't know what this is doing. Stop to check. Spyware. That's what we need. Okay. Again, another reason why loamy soils tend to be seen as more productive soils is they have an ability to hold more water in an available form. Of course, they also hold a fair amount of nutrients also. Okay, so I'm also going to talk about soils being biochemical reactors. Remember, we've got soil air, soil water, soil minerals, soil organic matter. All these things interact with one another. Soils really are biochemical reactors. Wide array of chemical and biological processes. I'll give you some of the basis of that a little bit later today, and then Dr. McGrath will entertain you with nutrient cycles this afternoon. I do want to tell you, though, that the soil-liquid interface, where liquids come to solids, is really where things happen. These surfaces allow for the absorption, this is adsorption with a D, of water and nutrients. Small particles have a whole lot more surface area than the same weight of large particles, so soils with clays are going to have a lot more going on. These surfaces are often charged, and the charge is typically negative. And if you're negatively charged, you're going to attract positively charged things called cations. So that's a little a view of what we're going to talk about later this morning. Before I finish, though, I just want to talk a little bit about soils as natural phenomena. If you're out hiking or walking somewhere, you probably realize that the vegetation changes over space, and if you were to look, you'd see that the soil changes over space, too. Here's a beautiful diagram of soils as they occur at the fall line between the Piedmont and the coastal plain. And it's trying to show you in a spatial way what soils occur in what different places. Well, why do soils differ across the landscape? I don't know if you ever thought about that or not, but why do they differ? And I think we can understand that it comes back to the fact that soils are a function of 5 things. We call them the 5 soil-forming factors. And soils differ across the landscape because one or more of these things differ. Okay? So soils don't all form from the same rocks or minerals. That's what we call our parent material. Soils aren't necessarily in the same landscape position. Some are on the top of the hill, the side of the hill, the bottom of the hill. That's going to affect what's going on here. Soils don't always have the same living influences, the same plants, for example, that live there. Climate and rainfall, temperature and rainfall affect how a soil develops, and also how old a soil is. How long has it been forming? Young soils, we've got old soils. Okay, so if we go back to this for a minute, we can see, and I don't know how well it shows up here, these soils here form from saprolite, which is weathered rock of a crystalline rock. Okay, so you see the Chester, Manor, and Glenelg all form from crystalline rock. But what's the difference between the Chester, Manor, and Glenelg? Parent material is the same, but what's the major difference? Huh? The landscape position, right? Okay? The Chester tends to be on the top of a slope. Your Manor's on a side slope, and your Glenelg is in a lower area. Okay? So what do you suppose happens to the stuff on the top, the stuff on the side, the stuff on the bottom? Yeah, you probably get runoffs. The materials from the top might go onto the side. The stuff on the side is going to not have as much water running through it because it runs off. Stuff's going to accumulate in the Glenelg. Okay? So there's a case where landscape position has a pretty dramatic effect on the soils that are going to form. Then you get over here, once you pass the fall line, and you can see that there's a mishmash of stuff. The Christiana, for example, forms on a clay, whereas the sunny side forms on a sand. Okay? Radically different parent material, different soils. Okay? Well, we describe soils out in the field by their horizons, and these are the ones that are recognized now. We've had some changes here over the past, well, I guess 20 years. Okay? O is an organic horizon. Cultivated soils typically don't have an O, but you'll find it in a forest, or you'll find it in a native grassland. It's a soil where the organic matter is very high in concentration. It's on top of the A horizon, which we would commonly call the topsoil. There's often an E horizon, where stuff has moved out of the topsoil, organic matter and maybe some clays and some oxides. A B horizon is what we typically call a subsoil. C is weathered parent material, and R in this case would be hard rock. Now, this is a simplified diagram. There are places where it's much more complicated than this. If you read a soil description in a soils book, you will clearly see more complicated descriptions than this. This is just kind of a gross generalization. Okay. Want to talk just a moment about soil surveys. Soil surveys is where you can find out what's going on in the soil beneath you, what it is, what its horizons are, what it's formed from, what grows good on it. Soil surveys have evolved phenomenally over the years. There used to be nice, tight little books with descriptions in the front and every map you want for that county in the back. They evolved from there into much bigger books, and this is a soil information only. You had a separate folder of maps. Okay, when soils were remapped, they fine-tuned the categories and found much more. Much more highly discriminated. Okay, and now it's moved into something called Web Soil Survey, where for most of the counties in Maryland, the books are antiquated now, and in fact, the soil survey information is found on a website called Web Soil Survey. The older system, where you actually had a book for a county or two, tended to have a very nice map of associations where you could get a generalized notion of what was going on in the area the book covered. This appears to be lost in Web Soil Survey. I can't find county-based association maps, but a lot of the other stuff is findable. Why would we use soil surveys or Web Soil Survey? Well, there's a lot of properties in it that you may need to know. You may need to know the yield if your producer has no idea what his yield is on a new piece of land. You're going to need to know drainage, class permeability, and depth of high water if you ever have to do a phosphorus site index. Just using and managing land, there might be some things that would be helpful. You know, where should I put the pasture as opposed to the cropland as opposed to the orchard? There's productivity tables. And of course, a major use of soil surveys was for engineering purposes, citing things like sanitary facilities, leach fields, building sites, roads, bridges, etc. There's a lot of information in there that's used far beyond agriculture. This information is all findable whether your county still has a soil survey book that's current or whether you've gone to Web Soil Survey. Regardless of which place you go, you'll find tables and tables of information of properties about every soil by name. Okay, soils have names. In this case, this is some physical and chemical properties of the soil: bulk density, permeability, how much clay, available water. Does that sound familiar? Stuff we just talked about, okay? Erosion, organic matter, okay? Many, many, many tables that organize the information based on the area of interest. I do want to mention that there's a lot of information communicated in a soil survey. First of all, soils have names. We saw that map where the soils had various names. Beltsville is typically a silt loam, okay? It has a symbol. Symbol is BE, Beltsville. So if you're good at soils communication and or you see a map with a BE, you know what it's going to be. And then there's also typically a letter after it where A, B, and C refer to the amount of slope a soil has where it's being mapped. So a BEB, you know, is going to have a greater slope than a BEA. You don't necessarily know what A and B means because across from county to county, the letters mean different things. An A, B, and C on the Eastern Shore is very different than an A, B, and C in Garrett County. Right? But you do know if you see a soil with a C after it that it is more highly sloping than that soil where it's mapped as a B or an A. So you can see here that the BEC, the Beltsville silt loam, is 5 to 10% slope, whereas the Westphalia fine sandy loam is 6 to 12. Not the same, but C is more sloped than A or B. An additional bit of information that you sometimes have, particularly in counties with more slope and more erosion, is a number after the slope. 2 and 3 indicate severity of erosion that's already occurred. Okay, you've got a highly eroded soil. So having a Westphalia a WAC2 means that there's already been moderate erosion on the soil. There's already been a significant loss of topsoil. 3 means it's pretty severely eroded. So there's a lot of stuff communicated with a minimum amount of writing. Okay, so here's a run through basic soils. I'll be back to talk to you later this morning about soil fertility and soil chemistry. If you have any questions now, I'd be glad to take them, though, before we turn the floor over to Dr. Felton. Does anybody have any questions? Please.
What's the relationship between the Web Soil Survey and the Soil Data Mart?
Soil Data Mart is where the tables appear to be stored. Hopefully anybody here from NRCS these days. It looks to me like Web Soil Survey is the spatial information and some of the more commonly interested, stuff that's of more common interest. But the real meat of stuff, you have to take a link away and go to Soil Data Mart. Yeah, it looks to me like you must use both to get the equivalent of what's in a book. Yeah, that's my feeling, having played around with it. Any other questions? Okay, good. Thank you.